Good afternoon, everyone. My name is Andy Neely, and I'm the Pro-Vice-Chancellor for Enterprise and Business Relations at the University of Cambridge. So in essence, across the university, I look after everything to do with innovation, commercialisation, startup spin-outs and links with business. I'm delighted to welcome you to this, our second digital Global Cambridge. For more than 5 years, we have taken Cambridge ideas to disparate locations around the world, welcoming groups of local alumni and friends. Now we bring Cambridge thinking and expertise to a wider audience than ever. In fact, this afternoon we have watching more than 850 people from 42 countries and all 31 colleges. During this session, your microphones and cameras will be turned off, but you can see and hear our speakers. And the speakers today are Professor Rob Miller of the Whittle Laboratory and Dr Masha Folk, currently working at Rolls-Royce, and they will each speak for a few minutes. We will then have about half an hour for them to respond to your questions. You can submit a question at any point. You don't have to wait until the end. Simply click on the Q&A box at the bottom of the page and type your question in. We're expecting there to be far more questions than we can actually answer. That's certainly been our experience to date, but we'll do our best to get through as many of the questions as we possibly can. The event is being recorded and we will share it on YouTube next week. It's worth noting Sir Frank Whittle, after whom the Whittle Lab was named, was the creator of the turbojet engine and as such the father of the modern aviation industry. Right now, particularly in these period of COVID, we find that particular industry, the aerospace industry, in a parlor state, thanks to the almost complete grounding of passenger fleets because of the COVID-19 crisis. But we're also well aware that in this era of climate change and diminishing resources, flight, and of course the engines that enable our magnificent aeroplanes to fly, must become more sustainable. Our land-based modes of transport too must emit less carbon. This is true for private as well as public forms of transportation. In 1973, Sir Frank Whittle opened the Whittle Lab. Ever since, it has been the preeminent centre for engineers working on streamlining and improving turbo machinery. Turbo machines are the principal technology for the world's energy conversion processes. Improving their efficiency is crucial as we seek to reduce the environmental impact of power generation and aviation. The Whittle Lab's research teams cover the gamut of turbo machinery technology, working closely with industry leaders to ensure their results are incorporated into future technological developments. Our speakers today are going to discuss their work in increasing the sustainability of turbo machinery. They are making great strides working on a range of technologies to decarbonise flight and land-based power, and the intention is that one day we will be able to make journeys without contributing to the degradation of our atmosphere. Professor Rob Miller is Chair in Aerothermal Technology at the University of Cambridge, a Fellow of Gonville and Caius College, Director of the Whittle Laboratory, Director of the Rolls-Royce Whittle University Technology Centre, and Director of the UK EPSRC Centre for Doctoral Training in the Future, Propulsion and Power. His research focuses on the decarbonisation of the aerospace sector and the power generation sector. He holds 11 patents and works closely with industries such as Rolls-Royce, Mitsubishi Heavy Industries, Siemens and Dyson. Dr Masha Folk holds a Bachelor of Science degree in Aerospace Engineering from the Ohio State University and a Master's degree from Purdue University. She completed her PhD here in Cambridge under Rob's supervision in February this year. Her research at the Whittle Laboratory examined the impact of combustor turbulence on turbine loss mechanisms. Masha joins us from Indianapolis, where she works for Rolls-Royce as a specialist in combustor turbine aerodynamics. So let me hand over first to Rob to talk a little bit about the Whittle Lab and some of his work.
Thank you very much, Andy. Can I have the first slide? Today I'm going to be talking about achieving zero carbon flight and land-based power. And more specifically, I'm going to be talking about how we can accelerate the technologies to meet that challenge. The Whittle Lab works on technologies for both flight and land-based power. Flight is responsible for about 2% of global emissions, but growing, and land-based power is responsible for about 25% of emissions. Next slide. For over 50 years, the Whittle Lab its primary focus has been on industrial impact. And I think this photograph here sums that up. So this is the opening of the Whittle Lab 50 years ago. And in the centre, you've got Frank Whittle. To his left, you've got Sir Stanley Hooker, who at the time was technical director of Rolls-Royce. To the left of him, you've got Sir John Horlock, who worked at Rolls-Royce and then became the first director of the Whittle Lab. On the right of Frank, you've got Sir William Hawthorne, who developed the combustion chamber on Whittle's first engine and went on to become the head of department in Cambridge. And on the far right, you've got Bob Fielden, who was the chief engineer on Whittle's engine. And he went on to develop the first land-based gas turbines at Rushton's in Lincoln that became Siemens UK and to develop the links with Cambridge. And over the last 50 years, we've built on this heritage, building strong strategic partnerships with Rolls-Royce, Mitsubishi Heavy Industries, Siemens and Dyson. And today, just under 10% of the total university industrial income comes in through the Whittle Lab. And the Whittle Lab is the world's most academically successful propulsion and power lab, winning 9 of the last 13 gas turbine awards, the American Society of Mechanical Engineers' highest award in the field. Next slide. Today, the Whittle Lab is focused on decarbonisation, and the scale of this problem is immense. So I thought I'd give you 2 examples of how you might decarbonise flight. So the first example is sustainable aviation fuels. And in this example, you take renewable energy and you use it to electrolyse water, splitting it into hydrogen and oxygen. And then you pull carbon out of the air and you put it together with the hydrogen to make a liquid hydrocarbon fuel. Now, this solution is a good solution for decarbonising aviation, but there's a problem, and that's the magnitude of the total energy required to do it. To give you an idea, if you took the largest offshore wind farm in the world, Walney Extension, off Blackpool, you took all its electricity, you could produce enough sustainable aviation fuel to power 3.5 return flights from Heathrow to New York a day. Let me give you another example. So say you took the route of a zero carbon emission plane. Now this could be batteries, but that would only take us a short distance. More practically, it's likely to be hydrogen. You would take the hydrogen and you'd store it at about 700 atmospheres in pressurized tanks. Now, that route has a factor of 2 or 3 lower energy use than the first solution, but there are whole infrastructure problems involved with bringing in that system. And currently, that technology has a limit, we think, of about 1,000 nautical miles. So you say in both cases, the problem's immense. And if we're going to meet the 2050 date, then really our enemy is time. Next slide. So about 8 years ago, we set out at the Whittle Lab to reduce the time it takes to develop technology by a factor of 10. And the blue line on this graph shows a conventional technology development process. And there's an inherent time constant involved with it of about 10 to 20 years to go from an initial idea to something making product. Now, if you could reduce that by a factor of 10, you'd move on to the red line and you'd ramp up much more quickly, but you'd also be able to test out more concepts. And that means you get a better final product. And we believe that the winners in this zero carbon world will be companies and countries who can adapt to technology change more quickly. Next slide. So about this time, about 8 years ago, I was out for a drink with a friend of mine, Tony Dickens, who was an aero tester at Red Bull Formula One. And he asked me what I was doing, and I said, we've just developed a second generation of 3D compressor blades for Rolls. And I explained them, and he said they were great. And then he asked me, when will they make engine? And I said, 6 to 10 years. And then I asked him what he was doing. And that day, he tested 20 rear wings He didn't understand how they worked, but he'd fitted a surface through the results, predicted the best, built it. It was the best in test. And it was a Thursday, and he just emailed this geometry to Track. And by Track, Red Bull had rapid prototype machines, and they made it that night, and it would be on the car for practice the next day. And at that point, the penny dropped, and we applied to the Aerospace Technology Institute, the government, and Tony Dickens left Red Bull and came to set up our rapid technology development teams in Cambridge. And you can see him on the right of that photograph with Whittle written on him. Now, how do we achieve this? Well, we set up small, sharp, focused teams, and this helps to break down natural communication barriers. So you can see in the photograph, these teams are industry and academics embedded together. We remove top-down management and bureaucracy, encouraging fast, bold action. But you also need to provide these teams with the right tools. And to do this, if you look at the left, so you have an idea and you have to be able to design it quickly into a product. And to do that, we use AI and augmented design systems running on graphics processor units, which design to industry standards in about 100th of the time. You then have to rapidly manufacture the concept. And the real breakthrough there was to take the manufacture process in-house and couple it directly to the design system. And this cut manufacture time from months to 8 hours for a full blade set. And finally, you have to test it. And in terms of rapid manufacture, rapid test, what we did was we did a value stream analysis of the test process, a bit like it's a baked bean production line. And we stripped out about 95% of the processes. And through this, we managed to get testing times down from months, first to days, and more recently, using pit teams, to about 15 minutes. In 2017, we did a formal trial with the ATI and Rolls-Royce, and we reduced the technology development time by a factor of 100. That was about 2 years down to less than a week. Next slide. So what next? Well, our aim is to build a new Whittle Laboratory to scale this process. And you can see a picture cut through that building here. And on the left, we want to have a space for embedding teams of industry and academics in one place to supercharge job growth. We also, in the same space, want to train the next generation of leaders. So all the PhD students from Cambridge, Oxford and Loughborough who are working in Propulsion and Power will spend a year in this space. In the middle, we're going to scale the rapid manufacture capability. And if you want to ask me about that later, there's some very interesting things there. And finally, on the right, we want to scale the rapid testing capability to about 80% of future aero need. So to sum up, I believe that to meet the challenges of climate change, it is critical that we fundamentally change the way we develop technology. Now, let me introduce one of the young engineers who is going to help deliver that change. Dr Masha Folk joins us live from Rolls-Royce Indianapolis.
Thanks, Rob. I'm going to talk to you today about the importance of taking a systems-based approach in developing technologies to solve these problems, which Rob had outlined for you. But before I do, I'd like to tell you a little bit about myself and how a girl from the Midwest ended up doing turbo machinery research in a lab halfway around the world. Next slide, please. Now, I had studied aerospace engineering here in the US at Purdue and Ohio State, and I was working for Rolls-Royce on one of our military engines, which power the V-22 Osprey. Now, that's that famous aircraft which can take off like a helicopter and then fly forward very fast like an airplane. And one day, the Marines who fly this aircraft flew them to Rolls-Royce, and they landed them in our parking lot. And we, as the engineers, got to go on board and meet the pilots who fly these things every day. And what struck me the most about that day was when the Marines thanked us for bringing together all of this complex technology into one vehicle, which they relied on to keep them safe. And it wasn't just my one component of the engine that did it, it was the entire system that was mission critical. And so I began to see that in order to get something so innovative like this vertical takeoff tilt rotor, you need to pull together a lot of technologies, a lot of complex technologies, and integrate them into a system. And that got me really excited about trying to change the world through engineering using a systems-based approach. So I sought out a graduate program that would allow me to do that, that would give me a broad experience in the technologies and their depths, but also how they came together. And so the reason I came to Cambridge, and the reason Rolls-Royce funded me to go to Cambridge, was because of this program, the EPSRC Center for Doctoral Training in the Future Power and Propulsion. Now, it's a collaboration between the universities of Cambridge, Loughborough, and Oxford in the UK, and also the 4 different industry companies which work in power and propulsion, Siemens, Mitsubishi, Rolls-Royce, and Dyson. And what's really important about this program is that through the experience at the different universities and their specific skill sets, as well as the expertise from industry, you really get to see a broad range of technologies and the deep technologies that are being developed, but crucially how they come together into a system and industry to make an impact in the world. Now, next slide, please. My own PhD research also took a systems-based approach inside the jet engine. So I looked at the interaction of different components. Now you see this jet engine, it's an incredibly complex machine. It's made up of a lot of components. And traditionally, all of these components are designed in isolation, the compressor, the combustor, and the turbine. But my PhD looked at bringing together the combustor and the turbine and looking at them as a system. And that's very important in terms of optimizing that system together. So I'm showing you here a photograph of that interface between the combustor and the turbine. Now the key role of the combustor is to mix together fuel and air. And as a combustor is doing this mixing, it creates an immense amount of turbulence. And you can think of turbulence in this photograph as these little clouds, these stormy clouds. And that turbulence then convects to the turbine, which has to extract work. And the presence of that turbulence changes the way the turbine works. Now, it doesn't matter what kind of fuel you're using, because whether it's a current fuel or a future sustainable fuel that Rob talked about, it's the process of mixing that creates this turbulence. So this interaction is an important one throughout all of these technologies. And actually what we found was that the presence of turbulence changed the loss in the turbine by 47%. And that was something that that wasn't known before. And so the American Society of Mechanical Engineers has recently recognized this work for contributing a fundamental knowledge to overall engine architecture. But actually, the gas turbine is not the only place where turbulence research is applicable. Next slide, please. I'm showing you here a photograph of an offshore wind turbine farm, and it's taken on a particularly humid day, and we can see the condensation in the air, and it illuminates the turbulence structures which can occur in a wind farm. And so there are about 80 turbines in this field, and most of them are sitting in the wakes and in the turbulence structures generated by that first row. And you can see that this is a really, really complex problem. It's one of the complex problems we're working on in the Whittle Lab. And it's complex because there's a range of scales. There's the scale of the turbine itself and the scale of the entire wind farm. And the interaction can be very complex. But by having researchers who understand combustor turbulence, but also researchers who are studying turbulence on a wind farm, we can hone in on the important mechanism that can allow us to optimize these complex systems and these complex wind turbine farms. Next slide, please. Now, for the rest of my talk, I'm just going to focus on giving you 2 examples of how we can achieve decarbonization in flight by bringing together technologies into integrated systems. And the first one I'd like to start off with is the embedded engine concept. Now, this photograph is it's a concept that was created by a collaboration between Cambridge and MIT, and they were looking at creating future aircraft with low drag and efficient performance. And there's a number of technologies here. You can see the wing and the wing tips, but I'd like to focus on the interaction between 2 technologies and their importance to the whole system. And that's the aircraft body and the engines, which are embedded in the back, which is very different to a conventional aircraft. Now, what happens here is as air goes over the aircraft, it is slowed down by viscosity. And that slow and sluggish air would traditionally create a large drag behind the aircraft. But what happens in this case is that the aircraft engines are able to capture that slow and sluggish air, re-energize it, and so that the system as a whole can perform much better. And aircraft like this and concepts like this actually require 20% less fuel. Next slide, please. When we think about purely electric propulsion, there are new challenges and opportunities that we can have. And in this case, I'm showing you what a medium range aircraft might look like that's purely electric. The biggest difference you see is that instead of two propellers, we have a range of distributed propellers on the wing. And that is made possible by electrification. And the key technology interaction here is the interaction between the propulsor and the wing. Now, in a conventional aircraft, and I have a schematic on the upper left-hand side, the wing, which generates lift for the system, is very far from the propulsor, which generates thrust. And the two are actually designed by two very different companies, and they do not interact. But when we have the freedom to distribute propulsion with the electrification, we can start to design new systems. And in this case, we can integrate the propulsor and the lifting wing together. And that allows us to extract a key interaction between the two. And we can provide more lift to the wing. And so, which actually requires less wing area for providing the same lift. So going from left to right, we see that the wing has gotten smaller. And in this prototype schematic, the wing is 40% smaller than a conventional aircraft. And that's very important for reducing drag and for extending the range of these electrical aircraft applications. Next slide, please. So I'd like to leave it off here, but I'd like to conclude that in order to achieve zero carbon flight and land-based power in the future, we really need to think about the deep technologies, but also how we integrate these complex deep technologies into innovative systems. And in order to do that, we need to train the new generation of engineers who are able to pull together this range of technologies and to apply them across all of the challenges in climate change. Thank you.
Great. Thank you very much, Rob and Masha, for those fantastic presentations. And just a small glimpse of some of the things that are going on in the Whittle Lab. As you've been talking, the questions have been streaming in thick and fast and appearing on the screen in front of me. And so I'll pull out some of those. I'll try and get to as many of them as I can. I'm not sure we'll get to them all, but I'll get to as many as I can. And I guess there are sort of three broad categories that appear in these questions. There are some around the technology, and we'll maybe start with that. There are some around regulation and the environment in which we might operate. And then there are some around that crucial bit about the collaboration between industry and academia. So let's start with technology, and I'm going to go to Atanu at Pembroke College first. So Atanu says, first of all, thank you for the great presentations, and then says the faster design cycle times are exciting and compelling. When do you envisage transatlantic longer haul zero carbon flight? So straight to the nub of the issue, Rob, when will we see this flight happening?
So that's a great question. So in January, we had we were lucky enough to have Prince Charles came to visit the lab, and he said during that visit that to tackle climate change, we needed to mount a military campaign. And I think that's a very interesting idea, because because the current aerospace industry, in my opinion, has been honed over the last 50 years for maximum profit and incremental gain without large technology shifts. Now, if you look back to those post-war years, you'll see the de Havilland Comet team, who developed both the first jet aircraft and the engine within 4 years to first flight. And if you look, for instance, at Kelly Johnson's team at Lockheed Martin Skunk Works, you know, in the late 1950s, the U-2 spy plane gets downed over the Soviet Union, and Kelly Johnson doesn't say, let's design a slightly better U-2. Within 4 years, his team has designed the A-12, which went on to become the SR-71. So I think that if we can do what Prince Charles says and we can really change the culture of the way we develop technologies, I think we can produce prototypes very quickly. I'm not sure that the current industry is set up to do that.
Great, thank you. And a linked one, David's asked, pointed out about the air routes in Europe. So air routes in Europe, typically about 800 miles, around half of all air routes in Europe, around 800 miles, 60% are within 1,000 miles. And goes on to talk about how close you think we are to having an e-powered or hybrid aircraft that could carry around 160 to 200 passengers. Rather than giving a timescale on it, do you think the development here is going to be smaller planes carrying smaller numbers of passengers in the first instance, going shorter distances? Is that the way this will pan out?
Well, so the number of people carried is not a problem. So what is the problem is range, and batteries will only get you a very short range. Hydrogen, I think we're looking at either through fuel cells or through gas turbines, and we don't know at what scale those technologies will work. But I think it's likely that up to 1,000 nautical miles you could do that. Now, it depends whether you go for a completely new aircraft or you decide to go for something at the A320 level, where you decide to put pressurized hydrogen tanks into something like that. But I think it's very doable. I think if we set up the right teams and we had the right approach, there's no technology barriers which would stop us doing it.
And could I just...
So I haven't given you a timetable there.
I think it'd be a hostage to fortune to give a particular time at this stage. Masha.
I just wanted to add to that. In the example that Rob mentioned, there are stepping stones in between these futuristic airplanes that I showed and changing some of the more conventional ones. So Rob talked about an A320 concept being used with alternative fuels, but also electric propulsion. And we've studied that concept of boundary layer ingestion for that type of a conventional aircraft. It doesn't need to be that flying wing. We've studied it for conventional aircrafts where you have an electrically powered fan at the back sucking in all of that boundary layer from the fuselage. And we've not only studied the aerodynamics of it, but we've studied the structural vibrational issues that might occur with that. So that technology is very close to being implemented.
Right. And then sort of building on this, I want to move away from timescale, but Kathy's asked, what are some of the material limitations that we might face for the decarbonisation of propulsion? Masha, do you want to start on that one?
Well, I think we're going to need a lot of dense power. So the gas turbine core is going to become smaller and smaller, and that drives temperatures in the gas turbine up. And the biggest challenge for temperatures is in the turbine, which is downstream of the combustor. And that's because they're already operating at, the temperature way above the melting point of the material. They're providing an immense amount of power, the same amount of power as a Formula One race car for one of these blades. So there's an incredible amount of challenge in improving that material. And I do think advanced materials will help us meet that cycle benefit.
Great. Rob, things to add?
And just to add to that, so I think this is one of the critical problems. If you're going to develop an aircraft which is going to make a major breakthrough, like Kelly Johnson did with the A12, you've got to bring together teams of material scientists, people who work in structures, chemical engineers on the fuel, and the turbine machinery people. And I think Cambridge is ideally set up for that. And this new Whittle Lab, we hope, will become the heart of solving these problems. So it won't just become a home for us, it'll become a home for anybody within the university who's taking on these challenges.
We talked a lot about aerospace and planes, but one of the questions Rosie's asked, which market will make the best use of hydrogen and have, in the sense of having the highest impact on reducing emissions? So do you think it is air transportation or the use of hydrogen for some of the industrial processes and domestic heating? Rob?
Yeah, so hydrogen to start with, is going to be hard to make in volume. And so you're going to reserve it for the things which are hardest to decarbonise any other way. So when people talk about using hydrogen for home heating, I don't think that's going to happen. I think it'll be electricity used through heat pumps in the home. I think the hydrogen we should use for things that we can't do any other way. And zero emissions short range flight is one of those things which is very hard any other way. So my bet, though we honestly don't know, my bet is that hydrogen will be reserved for those hard to decarbonise sectors.
Okay, great. And then Ian, related question, not so much on hydrogen, but Ian from Modlins asked, the aviation sector tends to major on carbon, yet this represents less than half the global warming impact of the sector. So goes on to say, what's being done to address other radiative forcing factors and NOx in particular? Rob, do you want to start on that?
Well, I was going to say NOx, but I was also going to say contrails. So obviously with aviation, you've got to take all three together. And there's some information coming out on hydrogen combustion that it might allow you to play some tricks on contrail formation, though obviously the water vapor is very high. But I mean, that's clearly going to have to be part of the problem if we're going to solve it. So, you know, any teams working on this, you've got to bring the atmospheric physics people in. At Cambridge, there's a very strong combustion team. And obviously through the CDT, we work with Loughborough, which is the National Combustion Centre. And they're doing a lot of work on starting to do work on hydrogen combustion. And that will play a critical part of this problem.
Great. So let's just switch from the technology for a second and talk. I might come back to the technology because there's some other questions on it, but I just want to raise up to the policy level. So David from Trinity College asks, to drive change, is the key priority human ingenuity or policy commitment? And I'm going to add to that list, or industrial commitment to make that change. Masha, do you want to start with that? Where do you see the key to making the change?
That's a very good question. And I think all of that, you know, all components of that are important because policy change drives industry and ingenuity. And you need, I think you need an avenue where you can bring ingenuity and industry together. And I think policy really will drive this. So policy and avenues for funding, you know, if we could fund more collaborations where industry and academia get to do the research, and that I believe stems from policy, that will make the biggest difference in accelerating these changes.
Yeah, and I mean, this is partly, it all strikes me, one of the things that's really great about Cambridge as a university is that ability to bring together people from very different backgrounds and disciplines to tackle those big systems type problems and to engage with industry and the policymakers to do it. And Rob, to some extent, that's what you're trying to do with the new Whittle Lab, effectively.
Yeah, that is. So on the technology front, I think the strength of the Whittle Lab is the ability to have a broad range of technologies and pull those together on the technology front. But I think if you're going to tackle, so the larger problem is an even bigger system problem. And that system problem includes delivery, scale up, infrastructure, investment and policy. And we've been working recently in the university on an idea called the Aviation Impact Accelerator, which brings together the new Whittle Lab with chemical engineering, and Dame Polly Curtis at the Cambridge Institute for Sustainable Leadership, and with our industrial partners. And that allows us to start to take on some of these policy technology problems. See, the problem with the decarbonisation of something like flight is it requires a policy solution, but that policy solution requires deep technology within it. And so you need that combination to get a roadmap that will work.
And do you just talk a bit about the timescale? So Andy has asked the question, what's the timescale on building the new Whittle Lab?
So we hope to start building the new Whittle Lab. We're shovel ready in October. We haven't got all the funds we need to do it, but we are ready to go. I mean, we are itching to scale this rapid technology development process. So yeah.
Great. Masha, particular question for you. I'm going to move away from the sort of broad regulatory thing for a minute, but back to technology. So particular question to you from Jeremy. You mentioned the Osprey. Is this the kind of model you see, vertical takeoff, but with electric propellers?
That is one concept that I think is important, especially if we start to think about urban taxis. And I don't know if that's necessarily a solution, but you need to consider the technology for where an aircraft can take off very quickly, and electric propulsion does allow you to do that. So it doesn't have to be urban taxis. It could be in areas that are difficult to get to without a runway. And electrification does give you that freedom, to integrate the propellers or to lift vertically. So yes, I think that is an important technology that we need to develop, that we could take advantage of when we bring technologies into future aircraft.
Great. Rob, you wanted to comment? And I know you're doing work with some of the taxi companies.
Yeah, so I mean, it's a really exciting area for urban air vehicles. And there's, over 100 companies globally working in this arena. And one of the really interesting things is by dropping the cost and timescale of technology innovation, it allows the Whittle Lab to not just work with the big companies, but to work with these small and medium-sized companies. So we're sort of building up a network amongst these companies to help them in this really exciting new area. And I think this will help with the systems problem, because some of these are good ways of demonstrating electrical technologies which will eventually scale up to larger aircraft. So it's an interesting arena.
And can we talked a lot about the sustainability and the decarbonisation agenda, but Rachel from Fitzwilliams also asked the question about the noise footprint of these aircraft. Does the technology improve the noise footprint for on-the-ground communities? And that's both at the large-scale planes, but also the air taxis, potentially. Rob?
Okay, so, I mean, clearly noise in urban environments will be the critical problem. But as Masha talked about, integrating components together. So traditionally, if you look at planes, the propellers or the jet engines are as far away from the wing as possible. And one company will design one and one company will design the other. And between the two, there will be an interaction, but it's second order. However, in these urban air vehicles, you start to get very closely coupled multiple propellers and airframes. And this is a whole design space that offers massive opportunity, but is completely unexplored. And one thing we've designed in the new Whittle Lab is a rapid test facility for combined propulsion airframe concepts. Because the idea that you would just build one giant model and test that one configuration, I think, is never going to let you explore the design space. You want to be doing what Red Bull did. You want to be testing hundreds of configurations a day. So the new Whittle Lab is designed to allow us to do that and explore these new design spaces and exploit these interactions. And this will be exploiting it both for lowering noise, but also for improving efficiency.
Great.
And could I just add, when I had shown the concept of the flying wing, I didn't touch on that technology, but the result of that wing and the engine interaction was a major reduction in noise. And so you often find that as you develop technology, the focus of that goes hand in hand. And we've demonstrated that. In fact, that one was called the silent aircraft because of its incredibly low noise footprint.
Great. Thank you. And linked to this, Keith from Trinity has come in and said much of the discussion seems to be built around massive national or international collaborations, big national centres and so on. Is there any room for small players, startups, to make revolutionary breakthroughs in this field? I mean, clearly, given the Cambridge ecosystem around startups and spin-out companies, we have a lot going on there. But I know, Rob, you are working with a number of the SMEs here.
Yeah. So actually, it's interesting. During COVID, we switched our rapid technology development teams from decarbonisation onto ventilator development. And as part of that process, we not only brought in the usual players we work with, we suddenly brought in departments, the Cavendish, chemical engineering, materials, civil, all came in and embedded in the Whittle. But we also brought in the wider SME community around Cambridge, and another number of people from those companies moved in. And then we also worked with Beko in Turkey, with Denel and DeFi in South Africa. And that was a real learning experience, because I think if you open up and you allow these small companies to come into the clusters, they really add something that a lot of the larger companies can't. And in that process, it was remarkable. Within a few months, we had a ventilator which is now starting to be produced. It's a clinical grade ventilator which is being produced by DeFi in South Africa, and that's at a cost point of about a tenth of other commercial ventilators. So I agree. I think bringing SMEs into this is really important.
Masha, can you comment from a Rolls perspective? I mean, I think the ventilator story, Rob, is a super example of how you manage very quickly to redeploy some of the Whittle capability to respond to the current crisis, and in collaboration with the SMEs. Talk a bit, Masha, about how Rolls-Royce engages its supply chain in some of these innovations and developments.
Absolutely. I think a lot of the innovation comes from ground up from these small companies. So, for example, one really interesting technology that we're considering is plasma control on low pressure turbine airfoils to make engines more efficient. And that really came about because there was a company that had made significant progress in this technology. And, I think they weren't a traditional supplier. It wasn't a traditional way of communicating, but we realized that we need to bring together a lot of different technologies for the future. So this sort of flow control example is all to lead back to, the need for companies and small companies and industries to come together. Now, in that example, that occurred very locally, but I think having a place like a Whittle, or a place where those technologies, having an avenue for those technologies to come together and those innovations to happen is very important. So where do you read about these ideas that you can integrate into your industrial product?
Just to add to that, Andy, I think post-COVID, we don't have the funds to do it the old way either. So it's not only an opportunity, but I think there are new models, and I think the way we can facilitate in Cambridge larger and smaller companies working together on some of these challenges, I get very excited about.
Yeah, well, as you know, I mean, that's one of the things we're trying to do with this whole of the sort of West Cambridge area as an innovation district, to make it a place that you can get large companies working with the startups, working with the university departments, and get that real exchange of ideas. Because I think about Cambridge's mission, it's all about contributing to society. The way we do that at scale is through collaboration, and that's the way we'll get the ideas out of the labs. And indeed, that's in essence Karen's question. So Karen from Emmanuel. So do you think industry and academia are working closely enough together? I'm aware of the strong UTC, University Technology Centre networks, previously worked at Rolls-Royce, but should we be doing more? Masha, what's your view on that? University and industry working together more closely?
Absolutely. I think traditionally it's very difficult to translate technology that's being developed in academia into industry, and that's doubly hard when you have to do it across the Atlantic. But if we had to think about the future of that relationship, I think we would take the Center for Doctoral Training program as a way to model after. And that's because you really get industry stakeholders into the research projects from very early on. And so in having that very fluid boundary between the two, that's what transfers the technology. So I took my PhD research into the company, and they had a spot for me right away to build on that research. So I had funding to pursue my own ideas from that PhD. And actually, within 6 months of being back in industry, I was back in the Whittle Lab as an industry person, testing ideas in the Whittle Lab. And so I think that's the kind of future collaboration between academia and industry to transfer technology faster.
So just to add to that, so any day of the week, well, pre-COVID, if you'd walk through the Whittle Lab, you would see Dyson people, Rolls people, Mitsubishi people, Siemens people. And it's those sort of relationships and the discussions over the coffee table about ideas where that's the gold dust. If you can grab those and rapidly develop those ideas, that's the magic.
And I think the exchange of people, I mean, it's both people, it's that free flow of people in and out of the Whittle Lab, and indeed the university more generally, and people then, for us, building on the Alumni Network. We have a fantastic Alumni Network with some really great people in fantastic organisations that we as a university want to collaborate with more closely. Let me go back to the technical piece for a minute. So Richard St. Catherine's says, can the panel comment on thermal management challenges of both battery and H2 fuel tanks and how much of a barrier to progress this is? And clearly thermal management challenges are significant with both of those. So Rob.
Yeah, I think this is a big growth area. So thermal management, either through passively or actively, is a critical problem, and especially in the air, the way you reduce the weight of these secondary cycles which are put in to cool the systems. And we're doing a lot of work in the lab at the moment for a number of companies in this area. Lightweight thermal management systems is a key enabler technology.
Masha, did you want to add to that?
I did. I just wanted to say that that's an example of technology that can also be translated across the industries. And so it goes back to what I was trying to say in training the engineers in deep technology, but understanding how that technology could be transferred. So we study heat transfer for turbine cooling and cooling these little components, but those same principles of heat transfer are equally applicable in these thermal managements of these larger systems. So it's incredibly important that as you train engineers, you point out that this isn't the only application. This is where you can really apply your knowledge.
And linked to that, sort of building on it, I think Pat from the US has said, do you see hybrid electric propulsion with conventional engines as the logical stepping stone? So this is thinking about a roadmap, really. So hybrid electrical initially, Rob?
Well, I don't know. I don't know is the honest answer. But there is, in hybrid cars, when you're driving them, there is a braking process, a re-accelerating process that's unplanned. Whereas in flight, you know what the flight cycle is, and you can recover some of the energy during landing. So the ability of hybridization to have the benefits that it's had in cars, I think, are lower. And there's another question about carrying around dual power sources. If you've got to carry around more weight is an incredibly strong driver in the air. But again, it depends very much on the scale you operate at. And we just don't know at the moment. I mean, clearly electrification is going to play a strong role, but whether that's completely electric or completely mechanical, or whether something hybrid in the middle works, I think is still an open question.
We had started exploring this technology, Rolls-Royce with Siemens and Airbus, and we were looking at the eFan X, and that was a concept where you had a gas turbine powering a generator powering electric propulsion. And I think we learned a lot from that, and that really helped us streamline our plan towards decarbonization. So I think it's a logical stepping stone that you probably have to go through to learn, and we'll learn a lot on our way to ultimate hybridization.
And you mentioned in their collaboration, so let me end with one final question. I'm coming to the end of the time, but Proti from Taiwan, ex-Trinity Hall, has said, are you seeking further international collaborations beyond the current setup? And if yes, what kind of resources or support are you looking for? Rob?
So I think it's yes is the answer. I think what's critical in doing things fast is the way you work. So there's a real danger when you put together large consortia that you drown in the meetings and the communications between them. So I think the real art is setting up the technical experts from the different centres so that they can work quickly and without distraction. You could imagine, especially during COVID, we had members of the rapid response team who were in South Africa, other members of the team who were in Beko in Turkey, ProDrive and the Whittle, and they were working together in a similar way. But you have to be really careful about the way you set these things up, otherwise you drown in bureaucracy, really.
Great, thank you. And apologies if we didn't get to your question. It's been a really thought-provoking 50 minutes or so. I'm sorry that we didn't have time to answer all of the questions, but I'm also conscious people will have other meetings and calls to get to, and so a short break between this one and the next one is probably sensible. Rob, Masha, thank you for your time and excellent both presentations, but also your answers to a wide range of questions this afternoon. It was really super to hear from you both. If you missed any of the Digital Global Cambridge webinar or would like to see it again, it will be available to watch on YouTube, as I mentioned at the start, so it will be uploaded there shortly. And clearly, you can send the link to friends and family who might be interested. They're bored of Netflix and want to watch this instead. That's fantastic. Our next digital event will be a Cambridge Conversations event when the Vice-Chancellor will discuss the effects of the COVID crisis on world economics. He will be joined by the Bennett Professor of Public Policy, Diane Coyle, and Mohammed El-Arian, the leading commentator and President-elect of Queen's College. And that event will take place on the 29th of July at 6 p.m. British Summer Time, and you can find further details on the website. So once again, thank you very much for joining us. Masha, Rob, thank you for your time and stay safe.